All right, thank you very much. Yeah, sorry for the little glitch. So I want to thank the organizers for inviting me. It's a pleasure to be here with you. I was in Kyoto like maybe 10 years ago for another instance of the TDA week, I think. Maybe the first one, I'm not sure, but so it's an even better, like greater pleasure for me. So this is a very long title. What I want to do is to approximate the persistent homology of functions in the case where we don't have access to the domain of the function. Okay, we have a sampling maybe of the domain, but we don't have a triangulation, so we don't have an explicit representation of the domain of the function. And for this, I'm going to use what I call functional geometric multifiltrations, which is a fancy name for something that some of you already know very well. It's just the name that I came up with. And I'll start my talk by speaking about those. So, and this is joint work with a few of my students. It started out as a project with an intern, Ethan André, and then it continued on with my PhD student, Jean Yili, and then David Loiseau joined us as a postdoc earlier this year, and he joined the project as well. There's a preprint on the archive. The preprint dates back to January, but there have been some developments since, so please wait for V2 before actually, I mean, you can download the current version, but you will see only half of the story, maybe only part of the story. Okay, can I move forward here? No, I can't. Let me use this. It doesn't work. Oh, wait. Okay, first. All right. So what do I call function? These function geometric multifiltrations. Those are generalizations of what we know as the function RIPS multifiltration. So here's the definition. So given a compact set X, and a function f from X to some Rn, I wrote Rd, but it's Rn. It will be Rn throughout the talk. So what you do is you build a RIPS complex, or the RIPS filtration, the normal RIPS filtration. And then at for every RIPS parameter, you filter the complex that you have by the sublevel sets of your Rn valued function. Okay, so that gives you a filtration with n+1 parameters. So again, d is n here, or n is d in this slide. So you get an n+1 parameter filtration. The first parameter being the RIPS parameter, and the rest of the parameters being the ones related to the codomain of the function. Okay, so that's the function RIPS multifiltration. And okay, so there is a special case of this filtration that has been heavily studied, which is called the density RIPS. It was actually introduced as early as the first paper on multiparameter persistence by Carlson and Zamoronian. And so where the function is actually a co-density estimator computed from some point cloud data, okay? So this filtration has been heavily studied, as I said, and here's a list of papers. And there are many related constructions that have appeared. There's the function check, the density check. There's the degree RIPS filtration. There's the kernel RIPS filtration, subdivision RIPS, subdivision check, et cetera, et cetera. And this, especially in the last few years, there's been an acceleration in the rate of publications on this topic. And for instance, this paper got the best paper award at Sausage 2 years ago. So I mean, this is a subject that really is hot to some extent. I can use only this to move forward, which is annoying. So what people have been interested in with respect to these filtrations is their stability. So it's well known that the RIPS filtration itself is stable under perturbations of the input point cloud. And so people have asked themselves, for instance, in the case of the density RIPS or some variant of it, can we prove that that filtration is going to be stable under perturbations of the input data? And some results have come out since the beginning of the year 2020. And these are three examples, sorry, coming from two different papers of such results. So these results are of the form, if I perturb my data, my input data, how is going to be the module that I produced in homology from this multifiltration going to be perturbed, and in what metric? Okay, so that's what people have been doing. So they were really interested in the stability properties of this construction. So now today I want to take a different perspective on it. I want to consider these multifiltrations in the context of statistical inference. So suppose my data is not arbitrary. My data are coming from some statistical process. Okay, so I have some measure, mu, that I don't know, that's supporting on a compact set X. And I'm drawing points P1 through Pk. K is going to be the number of points in the talk. And I'm drawing these points, maybe IID from this measure mu. And now I'm building this multifiltration from my point cloud. And I want to be able to say that this multifiltration is going to be an estimator of something, okay? A statistical estimator of something. Now, of course, if you go back to the previous results, so I hope I can go, yeah, I can go back, okay. If you go back to these results, what these results will tell you is that as the number of points goes to infinity, then most probably the points are going to cover the whole space X, and therefore these multifiltrations, thanks to these stability results, these multifiltrations will converge in homology to the corresponding multifiltration built on the space X, okay? So that is all nice, but then the target is not really the right one, right? The target is going to be this multifiltration that we don't really know what it is. At the end of the day, if you talk to a biologist and you tell them, hey, I have an estimator for this object, they will tell you what is this object, okay? So what they care about usually is more like the space itself, like the filtered space, the space filtered by this function f. That should be the target. And so that's what we're going to study. And in particular, we're not going to be able to say that the multifiltration itself converges to the space because that's not true. But we're going to say that the persistent homology of this multifiltration is going to converge to the persistent homology of the function f on the space X. Okay? And so this is very much in the same spirit as back in the years 2010, the algorithm Tomato, which was an algorithm for clustering, was doing precisely this. It was looking at the density rips bifiltration, taking vertical slices in that bifiltration and showing that as the number of points goes to infinity, then you can take the slice that you're taking, you can move it toward the vertical axis, and as you do that, you're going to converge to the persistent homology of the underlying density function the points were drawn from. In the same vein, there was a more recent result by Rolla and Skokola in their persistible paper, in which they are not taking vertical slices, but leaning slices, like diagonal slices. And basically, the slice straightens up as it goes towards the vertical axis. So in this work that I'm going to present, we are basically generalizing the results that are both in Tomato and persistible to functions that are valued in Rn, and now my d has become n, and it will remain so, hopefully, for the rest of the talk. And to do that, we're going to provide a framework to analyze these multifiltrations, in particular function checks, function rips, as estimators, okay, as statistical estimators of the persistent homology of the underlying function. All right. So So here is our setup. So we have a compact metric space X. So we're going to assume we have a metric. And we have a function that is Rn valued. And both of them are unknown. Okay, you don't know them. What you know is a finite sampling P of your space. And of course, you know the function values at the points of P, but not anywhere else in the space. And you know also the pairwise distances between the points. That's why I wanted to have a metric space structure in the first place. And your goal is to estimate the persistence module H of F, which is the persistent module induced in homology by the filtration of the sublevel sets of the function. Okay, so that's our setup. So here's a pictorial view. So here's the space X, which is the unit square in the plane. And then there's the graph of the function that you can see here. It's pretty noisy. And then I have this point cloud. That's my input together with function values given in color. And the input really is this point cloud. And I want to estimate the persistence of the function from that. Okay. So in a paper that we wrote in 2009, we actually considered the exact same setup. The difference was that the function was real valued, and today it's going to be Rn valued. Okay. All right. So I mean, everybody in this room who has taught TDA has already considered this problem in some certain context, and the usual approach to do that is to basically triangulate the space. Okay, so if you triangulate the space and you have fine enough elements in your triangulation, then you can build a PL approximation of your function. And then from this PL approximation, if you compute its persistent homology, we know from the stability of persistent homology that the persistence module that you will get from this triangulation will be as close as possible to the persistence module of the true function, okay, of the sublevel sets of the true function, where the distance between the two will be driven by basically the size, the diameter of the mesh elements. Okay? So this is really like TDA 101 level. But the problem with this is, well, in practice, you do not always have access to a triangulation. That's what I said at the beginning. I don't have access to a triangulation. Why? Well, because, for instance, X may not be Euclidean. X may have curvature, a non-constant curvature. So how do you triangulate such a space? It's sometimes possible, but it's usually cumbersome. Sometimes you just have access to a pairwise distance matrix in the first place in the context of data analysis. And so then, I mean, how do you triangulate anything from that? So, and even if you have access to like a better knowledge of the space, it might be very high dimensional. So building an explicit triangulation might be very, very costly. All right, so how do we proceed? Well, the natural idea when you don't have access to the triangulation is to take unions of balls, right? So that's what we're going to do. We're going to take the pre-images of the, I mean, we're going to take sublevel sets of the function. We're going to take their trace, sorry, on the point cloud. So P is my point cloud. F minus 1 of minus infinity T is the T sublevel set of F. And I'm going to take the trace of that sublevel set on my point cloud, which I can compute from my input because I have the function values on the points. And then I'm going to build balls, okay, of same radius, R, I mean delta, sorry. And I'm going to take the union of these balls centered at the points in this set, okay? So I get this filtration. So just to set up some notations, capital F sub T will be the T sublevel set of F, where T is an element in Rn. Oh, okay, N has turned to D again here, sorry. But D is N, supposedly. And then P sub T is going to be the trace of that sublevel set on my point cloud. And then the space at value delta that I'm considering is P sub T superscript delta, which is the union of these geodesic balls centered at the points of T and radius delta. Okay, so here's a pictorial view on the right. So the sublevel set is in gray, the trace on that sublevel set is in black, on the point cloud is in black, and then the union of the balls is shown in dashed. I mean, the balls themselves are shown with dashed lines. Okay. So how do you move? Yeah. So of course, yeah, if I move back, yeah, so you can easily show just using the triangle inequality that you have an interleaving basically between the sublevel sets of the function f sub t and this filtration p sub t superscript delta. Okay, that's very easy to show. You just use the triangle inequality, the fact that you're assuming f to be C-Lipschitz, because you need some regularity. So we're assuming f C-Lipschitz. In fact, in the paper, we're going to assume that f has a modulus of continuity, but for the sake of the talk, for simplicity, I'm assuming f Lipschitz. And then you get very easily this interleaving. It's like 4 lines of proof, nothing really complicated. And therefore, you can conclude that the persistent homology of F in any arbitrary homology degree and the persistent homology of this filtration of balls are C delta interleaved, where C is the Lipschitz constant. And again, delta is the parameter, the radius of the balls that you have chosen. So as you can see here, we're fixing the radius of the balls and we're filtering this union of balls by the function value. So we have an n-dimensional filtration, okay? Not an n+1 parameter, but an n parameter filtration. And we're comparing this filtration against the sublevel sets filtration of F, which is also n parameters. So of course you have to choose the right value of delta, and I'll come back to this afterwards. Okay, so this result is interesting, but it's not useful because, as I said, I'm not assuming I have access really to the underlying space of the data. And so I can't really compute explicitly a union of balls. It's just as complicated as triangulating the space, supposedly. So it's not very useful. So then we will make one more step forward. We're going to use Chesh complexes. So I'm going to replace at every value of t, I'm going to place, forget t, so if I have fixed delta, I'm replacing my union of balls by just its nerve, okay? And then if I make a further assumption, this time on delta, I'm gonna assume that delta is smaller than the convexity radius of my space, okay? So rho of x is the convexity radius of the space. So if I'm assuming delta is less than this convexity radius, then I know that the union of balls and its Chesh complex are homotopy equivalent, okay? And so I'm gonna replace the union of balls by its nerve, and I'm going to filter that nerve by the value t, okay, the values of the function. And of course, by the persistent nerve theorem, you know that the basically the family of spaces, so this filtration of balls and then this filtration of nerves are actually give isomorphic persistent modules. And so combining this result with the previous one, you get that you have C delta interleaving between the sublevel sets of the function in homology and the basically the filter nerve complex in homology. Okay. So this is cool because now we have a combinatorial object, the nerve complex, which we filter by the function values. But of course, computing this complex in general can be very complicated because you have to solve for k-fold intersections of balls. And if you only have access to the points and not really to the underlying space, again, we're back to square one. How do we compute this object? So the idea is to change the focus and not use the Chesh complex, but the Rips complex. And we would like to do the same thing. Like we would like to build the Rips complex for some fixed parameter delta and then to filter that complex by the function values. And then hopefully we'll get the same results. This we are not able to prove. So instead, we're using a pair of Rips complexes with parameters that are different that are related by a factor of 2. Okay, so we build two Rips complexes, one of parameter delta that you see here, one of parameter 2 delta that you see on the right, and then we filter them by the function values. Okay, so and then what we're interested in, so this gives us two persistence modules, and of course one of the filtrations is included in the other, so you have a morphism of persistence modules induced in homology. And what we do is we take the image of that morphism. So basically we take the generators, the persistent generators in the first filtration, and we're looking how they behave when we go to the second filtration. Okay. All right. So here's the result. So the theorem says the following. So if you choose your delta well, right? So there's a caveat here. There's a hyperparameter delta that you need to choose. Let's assume we have an epsilon sample, like P is an epsilon sample of X. So the Hausdorff distance between P and X is not more than epsilon. And under this assumption, if we choose our delta within the range 2 epsilon to the convexity radius of X over 2, okay, so that's a pretty large range as epsilon goes to 0. If we choose the delta within this range, then basically this module phi, which is the phi delta, which is the image of the persistence module of the Rips parameter of parameter delta into the Rips of parameter 2 delta. So this phi delta as a persistence module is within distance 2c delta of the persistent homology of the function. So here I finally have an estimator that I can compute from my data, and which is going to converge, hopefully, to the target, h of f, as epsilon goes to 0, so as the number of points goes to 0, provided I choose a delta within this range every time, and I let delta go to 0 as well. Okay, but delta should go to 0 at the limit, but not too fast, because if it goes too fast to 0, it will fall out of the range 2 epsilon, especially it will become smaller than 2 epsilon, which is forbidden here. Okay, so this result really means that as an estimator, phi delta is consistent, it's converging. Okay. So here's an example. So going back to the, before that, I should mention that this result actually is not new for the case where f is valued in R, because that was proven in 2009, but as the case where n is greater than 1 is actually new. Okay, so to go back to the illustration that I gave earlier, so here's our setup, and then the result that we get is this one. So as you can see, we're approximating not the persistent homology of the function, but of its opposite. And so in degree 0, so that means that we're taking the super level sets. The theory is the same, but it's just because it's more interesting to approximate the super level sets of this function. And if you try to look at, if you draw the graph of minus f, it's much less pleasant than the graph of f. So that's why I chose to draw things this way, which is a bit weird. But, okay, so you have the graph of f here, and then you're approximating the persistent homology of minus f. And in that case, what happens is that, of course, in the super level sets, you should have 6, in degree 0, you should have 6 prominent bars, because you have 6 peaks, 6 main peaks in the graph of the function. And then you also have one of them that is on the rim of a crater. And so you should see the crater appear as a generator in H1. And this is what we see here. Plus, there is some noise, of course, and the noise is because we're using a sampling. Okay. Here's another example, just to show you that the method is not restricted to points in the plane. So here now the points are on a torus in 3 space. And then the function is the one that has the one whose graph is given, is color-coded here at the top, on the top right corner here. So you see that it has 4 peaks, and there's a number of saddles here. and there are a few more saddles around here, and there are some minima over here. Okay, so now I'm looking at the super level sets of the function again. So I see 4 main bars, which correspond to the 4 peaks. In each one, I see 5 main generators. The reason is that each one of these peaks will generate, a handle. So there are 4 handles, plus there is the tunnel. So that's why we have 5 main bars. 2 of them are actually essential classes. So they correspond to the homology of the torus. And then, of course, in H2, I see an extra bar that appears somewhere in the lower parts of the filtration. And that is the essential class of the fundamental class, sorry, of the torus. These 2 examples are for n equals 1, so for real valued functions. Now, if I move to n equals 2, here's a very, very simple example so that we understand what happens. So I take a circle, and I sample the circle uniformly at random. And then I take, as my 2 functions, I take the projections onto the 2 coordinate axes, okay? So the first function is just the abscissa of the points, and the second function is just the ordinates of the points. And now I'm computing homology in H1, and here is the result of the approximation of, this is phi delta for a well-chosen delta, so a delta that is large enough so that the circle gets connected, but not too large, of course. And so for that magical or good choice of delta, I should say, then I have these persistence modules as my phi delta. And this is very close to the ground truth being the exact same persistence module, which is a free module, which is generated at 1, 1. In order to see the circle, like the loop, you need to take a super level set for a level that's at least here, okay? Because below that, you will miss either this part or that part of the circle. Okay, so you really need to put your T here or above to actually start seeing the circle, and that's why you get a free module as your ground truth. Finally, another example where this time n equals 3. So this is taken from a paper by Oliver Vipond and co-authors from 2021, where they looked at, it was an applied paper. They looked at some data set in immunohistochemistry. I won't go too much into the details, but they look at in the plane, in the unit square, the distribution of certain types of proteins in some aggregate of matter that they had pictures of these aggregates, and they looked at the density of the distributions of certain types of proteins in this aggregate. And so to study the densities, they use a density estimator. Here it's a Gaussian kernel estimator. And they studied 3 proteins, CD8, there was, what are the names of the other ones? CD68 and FOXP3, don't ask me what they mean, but there are 3 different proteins. And so they used an estimator for each one of them. So they have 3 real valued functions, which they combine into R3 valued functions, okay? A function valued in R3 over the unit square. Okay, so now we take a uniform sample, and we want to study the persistent homology of that R3 valued function. So we now compute, we sample the square uniformly at random with more and more points. We start around 100 points and we go up to 1,000. And then we study the evolution of the distance between the persistence module phi delta and the persistence module h of f, where f is again this R3 valued function. So you might ask, how do you get the persistence of h of f if you don't know f? Well, we're in the square, so we can lay out a grid that is fine enough so that this TDA 101 approach that I mentioned earlier just works. Okay, so that's how we get a proxy for our ground truth. So this is the evolution of the distance between the modules. How do we compute the distances between modules? Well, these are modules with 3 parameters, so this is much more complicated than with modules with 1 parameter. So what we do is we use an invariant. The invariant we use is called the Hilbert measure. It comes from a projective resolution of the modules. And so what that means is that, and it is a stable invariant in the 1 Wasserstein distance. So what we see here is actually a lower bound on the real Wasserstein distance between the modules. Nonetheless, we see that this lower bound, we could take 0, right, as a lower bound, so we could be cheating, but we hope that we're not cheating here, but by taking a lower bound. Nonetheless, and anyway, the lower bound actually seems to go to 0 as the number of points goes to infinity. All right, so that's the state of affairs for this first part of the work, and of course there are many questions that are raised here. So the first one probably is this delta, like we have this parameter delta, so we would like to get rid of it. And how do we choose delta in practice? So there are 2 answers to this. The first one is the statistician's answer, which is to say, well, I'm going to do statistics, and I'm going to choose the best delta with respect to some convergence rates, basically. Okay, and this we studied, actually. There's another approach, which is to say, hey, we're doing TDA, and in TDA, we're used to not choosing deltas, usually. And so we're going to look at the full n+1 dimensional persistence module if we let delta vary. And we're going to study this guy. We also did this, and so hopefully I'll be able to present both approaches. Of course, what this result says is that we have a convergent estimator, and we would like to get some convergence rates. So I will show you one result on this. And then there are other questions like how stable is this with respect to input noise in the input? Because we're assuming here that we have exact function values and exact pairwise distances. And this is not reasonable in practice. In practice, you rarely have exact measurements. And even like the distances, since these are intrinsic distances, like geodesic distances, this is even worse. Like usually you don't have exact geodesic distances. So we have to be able to show that these results still hold under perturbations of the input. And the answer is yes. I refer you to the paper on that, not the version that is on the archive, but the V2, which is going to come out soon, because we studied this stability. And then, of course, there's the question of computing the invariance, because if you think about it, phi delta is not your regular persistence module coming from one filtration. It's actually the image of a morphism between two persistence modules. So how do you compute invariance, such as, for instance, these Hilbert measures from these guys? Like the current software does not enable you to do it. So I don't know. I have some slides on this, but I'm not sure I'll be able to talk about it. But anyway, we have a way to do it. And finally, there's this question, why did we use a pair of Rips complexes and not just a single Rips complex? And this is the first question I'm going to tackle right now. I'm going to show you why. So first of all, there's a historical reason for this. In the paper in 2009, the one that was considering functions valued in R, the authors were using a pair of Rips filtrations, Rips complexes, not a single Rips complex. The reason was because the year before, we actually proved that if you wanted to infer the homology of a compact set from the Rips complex, you needed two Rips complexes in general, not one. And so that's why in 2009, we decided to use a pair of Rips complexes, but we never questioned that choice. And now that we're coming back to the same problem 15 years later, we're actually questioning this choice. Do we really need to use a pair of Rips filtration? So here's an experiment that we made on synthetic data. So this data is in the plane, and as you can see on the top right corner. And you can see the data are concentrated around 3 annuli, plus there is some scatter noise. And on the left-hand side, you see the graphs, the evolution of the bottleneck distance between, so what is the function, by the way? The function is the height function. So it's the height with respect to the ordinates, okay? So it's a R-valued function. So then in homology, you get a one-parameter persistence module, so you can decompose them, and then you can compute the bottleneck distance between the barcodes. So here, what you see is a plot of the value of that bottleneck distance between this and the ground truth, I mean the estimator and the ground truth, as delta evolves, okay, from 0 to whatever, say plus infinity, but plus infinity is 0.3 in our case, okay? This is for the image module, so the one that I was using before. And at the top is the plot that you get for a single Rips complex, okay? So 2 observations. First of all, look at the scales on the left-hand side, because this guy here seems to, at the top, seems to start much lower, but actually they start at the exact same value. It's around 2.5, okay? And then instead of going down and then up again, so having this typical U shape where you say, before here, you're not within the right range, so you get something that is much like a distance, an estimator that is much wilder than it should be. Then you get into the right range, and so your estimator is much tamer. And then you, as delta increases, of course, the distance the distance increases until you actually step out of the right range, and therefore, again, your estimator becomes wide. So this behavior that you see at the bottom, which is the behavior of phi delta, is the one you would expect from the estimator. At the top, you have a similar behavior. You have this U shape in the central part. On the left, we don't control much, but anyway, and in the central part, we have this U shape. And as you can see, it actually goes to much higher values. So the distance from the estimator to the target is much, much higher than what we get with the image Rips. And now if we look at the actual persistence modules that we get, so here's a representation of these two modules. So on the right-hand side, you have the persistence module phi delta for every single value of delta within the range that we consider it. And on the left-hand side, you get the same thing, but for a single Rips complex. And as you can see, so what are these colors? So basically for each delta, you take the vertical slice, okay? And now you restrict this picture whatever it is, to that vertical slice. And then the colors are actually giving you the bars in the barcode, okay? So here on the right-hand side, you see that there are few bars and that they are very stable across different choices of delta. On the left-hand side, well, there is much more noise for every single value of delta, and also the bars themselves might actually behave erratically from one value of delta to the other. Yeah, question? No, the colors don't mean anything. It's just to discriminate between the bars. So this is not a multiplicity. This is just one bar, actually. And then this is one bar, and then that is one bar. So, but then that's the upcoming story. The fact is that all these bars together, like these occurrences of the same bar across different values of delta, they do actually correspond to a single component of the n+1 parameter module. So you can actually collate them together and get a single thing here and say this thing corresponds to, say, that would be the lowest circle here on the top, the lowest annulus. And then this would be the intermediate annulus, and then the one at the top would be corresponding to the top annulus. Yes. Yeah, there's something there. Yeah. And yeah, exactly. So I'll come back to this afterwards, but yeah. On the left-hand side, there is much more noise. So maybe there is some consistency across scales. It's not very clear if this happens, but anyway, you see that the filter RIPS is much noisier than the image module phi delta. Nonetheless, this is just empirical evidence, and I have no actual proof that the filter RIPS doesn't work. And the reason why I don't know why it works or not is that if you forget about the function and just care about getting the homology of the underlying space, then it's known that if you put sufficient regularity conditions on that space, you will be able to recover the homotopy type of that space for certain RIPS complexes. And this is work by, for instance, Henry Adams and other people in this room. And so now if I put a function and I look at the sublevel sets of the function, what may happen is that close to critical values, the sublevel set will behave erratically, more erratically than anywhere else. So probably the conditions for these theorems to apply will not be met. But then that would happen only very close to actual critical values. Outside of these these nasty ranges, for most of the values, I would have a good behavior of the sublevel sets, and therefore the RIPS complex would actually approximate them well, probably. Yeah. So the question is really open, and I would be very happy to see. I mean, I would be so happy to be able to say that the picture on the left-hand side is just it's just noise that's added to the true picture, where underlying this, there are 3 blocks like these ones here. It's just that I can't see them. Okay. So this is all for the question about using a pair of RIPS complexes. Now the next question is, how do you choose your delta in practice? So you can choose a delta and then hope for the best, or you can try to leverage these pictures, actually. Okay. So how did we generate these pictures, by the way? So what you see, these plots here are the plots of an invariant that is called the MMA. MMA means multi-parameter persistence module approximation. So it's an invariant that was defined by Mathieu Carrière. And what it does, basically, the vanilla version of MMA takes diagonal slices, restricts the module to these diagonal slices, and then from one diagonal slice to the next in the sequence, it actually uses Vineyard to try to match the bars together. Okay, so each slice gives you one certain barcode, because it's working only for bifiltrations, by the way. So each slice will give you a barcode, and then from one slice to the next, it tries to match the bars using the Vineyard algorithm. Okay. Here we're using a variant of that version of that algorithm, of that invariant, which takes vertical slices for obvious reasons, because our estimator uses vertical slices. So that's why we're using this. Okay. And so the question is, like, we see 3 blocks. So basically we see that the Vineyard algorithm really was able to match this bar with its analog in the next step, and then in the next step, etc. Is this just luck because the bars were so different? Or is there something deeper there? Is it true that you can actually match the bars together from one delta to the next? Okay, and this is our second result that is coming up. So to state the result, I need to change my target because now I'm going to look at the full n+1 parameter multifiltration. So with the first parameter being the scale parameter, and then the rest being the parameters coming from the codomain of the function. So I have an n+1 parameter module that will serve as an estimator. So what is the target? Because the target was n parameters. So how do I compare an n+1 parameter module to an n parameter module? So what I do is I'll just kind of extend the h of f from Rn to Rn+1, which is really the same thing as saying, well, I place copies of Rn in each vertical slice here for each value of delta, and then I put identity maps between these copies of the vertical hyperplane. Okay, so the mathematical operation to do that is just a kind of left-hand extension of the inclusion of Rn into Rn+1, where Rn is mapped to the vertical axis. Okay. And this is my new target. So it's if my persistence module had a single bar, initially, if it was a one parameter persistence module, so n equals 1, then if it had a single bar here, that bar would become this rectangle here on the right. Okay. Now, my new estimator is the full n+1 parameter module phi, which I call phi. So phi is basically given by taking phi delta for every single value of delta. And of course, there are natural morphisms between the phi deltas for different values of delta. Those morphisms come from inclusion in homology. And one way to see that module is as follows. So you take the function RIPS multifiltration, okay? And then you smooth it horizontally along the first axis, and you smooth it by multiplicatively, not additively. Okay, so each phi delta is actually mapped into phi 2 delta. Okay, and so this horizontal multiplicative smoothing gives you the module phi here. So it's a smooth version, if you want, of the RIPS multifiltration, well, the module induced in homology by the RIPS multifiltration. And here's a result. So the result is that under the same assumptions as before, so on the regularity of the space, on the regularity of the function, then what happens is that if you choose a vertical slab, this time not just one slice, but a slab, inside each slab of the form 2 epsilon delta 0 for any delta 0 that is within 2 epsilon and rho of x over 2, then the restrictions of the modules phi and the target to that slab are going to be intraleaved, 2c delta 0 intraleaved, but the intraleaving is not the usual one. It's not diagonal intraleaving, it's actually vertical intraleaving. They're intraleaved vertically. So here is a picture of what that means. So for every value of delta, if you take the restriction to the corresponding vertical slice, you have the intraleavings, the 2c delta intraleaving coming from the previous theorem, okay, for every value of delta independently. But then what this new result says is that these interleavings, these vertical interleavings, are actually natural in that, and so that they commute with the horizontal morphisms in the two modules with n+1 parameters. So why do we care about having a vertical interleaving? By the way, having a vertical interleaving is a slightly stronger condition than having a usual interleaving. Why? Because if you have a vertical interleaving as shown here at the top, then you can compose the vertical interleaving maps with the horizontal morphisms to get a usual interleaving. And because interleavings are measured in the L infinity distance, that will not change the value of epsilon. So already vertical epsilon interleaving implies diagonal epsilon interleaving. But why do we care about these vertical interleavings? Well, I'll tell you now. We care when we look at invariance, okay? So if you take an invariant of persistence modules that you know is stable under the usual interleaving, because a vertical interleaving induces diagonally a usual interleaving with the same amplitude, then you have a bound on the distance between the invariance of the estimator and of its target in terms of the Lipschitz constant of your invariant, if your invariant is stable, and multiply by this bound that was here, okay? It's actually 2c delta 0 here, sorry. Okay? But this is all good, but if you think about it, if your function is not sufficiently regular, this is actually a trivial result. Why? Because you're considering a slab with left side at delta equals 2 epsilon, with right side with delta at delta 0. And now, if your function is, say, 2 million Lipschitz, okay, it's Lipschitz continuous with the Lipschitz constant that is 2 millions, then basically if you restrict your two modules to that slab, they will, for obvious reasons, be the delta interleaved, because delta is so large that, I mean, the Lipschitz constant is so large that you will never be able to go from one module to the next module to the first module again without jumping out of the slab. So for trivially, you will get such an interleaving if your function is not regular enough. But of course, if the function is very regular, if C is very small or small enough, so smaller than this value, then this result is non-trivial and you've got this guarantee. Now we care about vertical interleavings for this reason specifically, because there are some invariants that actually behave very well under vertical interleaving. So there's an invariant which is the multigraded Bailey numbers. So the multigraded Bailey numbers are the locations of the generators in the terms of a projective resolution of the modules. And this invariant, which has been considered for a while in TDA, it was proven to be stable under perturbations of the modules in the interleaving distance, where stability is measured in terms of a certain bottleneck distance between the locations. Well, you see basically the multigraded Bailey numbers as measures, as sign measures, and then you can assign, you can define a Wasserstein distance, or Wasserstein distances on these sign measures. And under these choices of distances, you can show that the invariant, the multigraded Bailey numbers are stable. So this was a result by myself and Luis Cocola in 2024. And then what we did in this paper was to just reread that result and say, what if we have a vertical interleaving instead? And basically, it turns out that the proof is exactly the same. And so the invariant behaves very well under vertical interleaving. So here's an illustration of this. So let me take, again, a very simple example. So I take points uniformly sampled along a circle in the plane. And my function is just a height function with respect to the ordinates. Okay, so it's shown on the top right. And now what you can see on the bottom left is, first of all, in magenta, you see on the left-hand side, so this bar that you see outside of the plot on the left, this bar is the barcode of the ground truth in H1. So we're using H1 homology. So what happens is that if you look at the persistent homology of the height function on the circle, then nothing will happen in H1 until we reach level 1, precisely where there is the cycle, the fundamental class of the circle that appears, okay? So that's why the ground truth in this case is just this infinite bar starting at height 1, okay? Now we can extend this ground truth to a 2-parameter module, and so we get the free module that you can see in magenta in the plane here, and so this is the free component. This is the free module. The target now becomes this free module. And now here are the persistence modules in green and yellow. The persistence modules that you get from, first of all, so in yellow, that's the persistent module that you get from the function RIPS multifiltration. And in green, it's the module that you get from the function RIPS multifiltration, where the parameter delta has been multiplied by 2. There's a rescaling of delta. Okay. And now our estimator phi is actually the smoothing of that thing. So it's basically the image of the yellow into the green. And that you can see on the right-hand side in blue. In blue here, you see the persistence module phi. Okay, so that's our estimator. Now, first of all, first comment, this example is so simple that all the modules are interval decomposable, so I can represent them exactly. These are not invariants. These are the actual modules, or the summons of the modules. First comment. Second comment, as you can see, on the right-hand side, the blue, the estimator, phi, does approximate in interleaving distance the ground truth within a certain range, which goes from 2 epsilon to pi over 3, where 2 epsilon, well, epsilon is the value of the density of the sampling, okay? So here you see the bound 2 epsilon, and then here what you see at pi over 4 is rho x over 2. Okay, so we have a guarantee for approximation between 2 epsilon and pi over 4, and it turns out that the estimator still approximates fairly well the input until pi over 3. Okay, but there we're not able to say anything. But here in this range from 2 epsilon to pi over 4, we have the theorem. This is an illustration of the theorem. Now, what you see here is a closer look at what happens at the frontier between the two modules. So this is the bottom of the target, and this is the bottom of the estimator in blue. And as you can see, if you now look at the multigraded Bailey numbers of the restrictions of these guys to this strip here, what happens is that the free target has just one generator here, right at the boundary of the slab, the left boundary of the slab. And then there's a corresponding generator here in the estimator. And this is coming from the vertical interleaving and the fact that the multigrid numbers behave well with respect to interleavings. So what the result says in the previous slide is that you can find a matching between the generators and the relations, basically, of the two modules, such that every generator is actually matched vertically with its corresponding generator in the other module. And you see this vertical matching. So, okay, so why are these two guys matched together, whereas they come from the same module? That's a long story. To make it short, it comes from the fact that the measures that we get are sign measures. Anyway, so I'll stop here with this example and with this result. Oh, yeah, maybe I want to show again, to go back to the previous illustration that I had to motivate the result. So the result really says that we should see three things here, okay? It's not just luck, it's not chance. We saw three components in the MMA because there are three, I would say, there are three summons actually in the underlying module. And one last illustration to really explain the difference between this result and the previous one. Look at the top left here. So we have three circles in the plane again, and they're of different sizes. The function is, again, the height function. So this circle here appears at -6, more or less, in the sublevel sets. This circle at -2, and that circle around 0. Okay, and so now we get this sampling where the smaller circle is sampled much more finely than the intermediate circle, itself sampled more finely than the bigger circle. And so because of this, we have in the estimator, there are three components. Okay, there are three summons. The first one is in green here. It corresponds to the smaller circle, which appears first and then dies first as well. At the time when the second circle dies in terms of distance threshold or delta parameter value, at the time when this guy dies because it gets filled in the Rips complex, this guy appears. Okay. And so it's born exactly at the same time. And then at the time where this guy dies, this one appears, okay? So of course, it's a very specific conjuncture of events, but this is a typical situation where if you restrict yourself to vertical slices, you will never be able to see that there are actually three circles or three components, okay? Where that's what you would see basically with just vertical slices, because at every point, at every parameter value delta, if you restrict to a vertical slice, you see one bar. So the natural hypothesis you would put in that case would be this one. Okay. But actually what happens is that there are three things. And this is why the second theorem is so important. Okay, I want to know how much time left I have because I want to leave some time for questions. I think it was until 10:10, but okay, so I'll try to be quick. I think I'll skip the algorithmics. Unfortunately, the algorithmics, I mean, the idea, the message is you can actually reduce the problem to the standard problem of computing presentations of modules. Okay, so the idea is if you want to compute invariance from your module, from this phi, a good approach for this is to compute a presentation, because most of the invariants that people consider in practice are actually deduced from presentations. Once you get a presentation, you have an algorithm to compute your invariant. So basically, the task that we set ourselves to do is to compute a presentation of our module phi, which is again the image of a certain persistence module into another one. And the message behind that part is to say, well, basically, you can do a trick. You can do a trick so that you reduce the problem to computing just a presentation of a module induced in homology from a single filtration. Okay, so that gets rid of that part. So now I can conclude with the statistical analysis. So to get some convergence rates, we have to make some statistical assumptions. So far, I didn't make any statistical assumption. I only assumed that, I only got results which were geometric in nature. I was assuming that P was epsilon close in Hausdorff distance to the domain of the function, okay, deterministically. And now I'm going to make some statistical assumption, which is that now my points, I have K of them, they're sample IID from some measure which is supported on X. So if I don't make any assumption on the measure, on the regularity of the measure, I'm pretty doomed. There could be very nasty things that happen. The measure could be like concentrated in hotspots, and I have zero chance of sampling the whole space with that. So I'm going to make a regularity assumption, and the assumption I'm making is very standard, so to speak, because it's to say that the measure is AB standard. So this AB standardness condition is a condition on the growth rate of balls in terms of the measure. Okay, so the balls don't grow too slowly in terms of mass. Okay, so by the way, all this is actually very standard. So basically, you take the results that we had, okay, that I showed you earlier, and then you combine those with standard results in sampling theory by Cuevas and co-authors, and you get this. Okay, so this may look daunting to some of you, but this is really just plugging in the convergence results that we had previously, which were deterministic, with results on the sampling results on basically support estimation from measures from point cloud data, from point samples, and you get these results directly. So, and this is the same as what was done in the one parameter case by people like Larry Wasserman and then Frédéric Chazal and then co-authors. It's basically the same thing. The only difference here is that we have this choice of parameter delta to make at some point. So we need to find the optimal. We need to use an optimal choice of delta, and luckily for us, there is such an optimal choice. If you assume you know A and B, well, that's a strong assumption, because that means that you know the growth rate of the ball. So you know in which class of, say, complexity your underlying domain is. But OK, if we know that, then we can set delta to this optimal value, which is of the order of log k over k to the 1 over b. OK, b here really acts as the dimension. So if you assume your measure is the uniform measure on some manifold of dimension b, then this is the same b as you will see here. OK? And so under this assumption, we can choose this optimal delta, and we get these deviation bounds. Okay, I mean convergence rate. Sorry. And so you see that the convergence rate is bounded. I mean the deviation from the target is going to be bounded above by something that is of the order of log k over k to the 1 over b. Okay? And you can prove that any estimator would be at least within 1 over k to the 1 over b. So there is a little gap between the two, which is of the order of log k to the 1 over b, which is kind of negligible compared to the 1 over k, but still there is a little gap. Some people in the one parameter case actually worked hard to fill in this gap. We can probably do the same thing here, but we're too lazy to do it at this point. All right, so this raises a number of questions. So first of all, what this says is that phi delta k, if you choose your delta well, and you take a single vertical slice, and you build the estimator from this single vertical slice that you have chosen well, then you get an almost minimax optimal estimator. Okay. If you don't know what the value of delta k is, which is the norm in practice, you won't know A and B. So to do that, there are procedures using subsampling that people have been using in the one parameter case. You can use such a procedure to actually infer a good value of delta k. Okay. Of course, these results are stated for phi delta k, but there are some, I mean this one, but there are some analogs for phi itself. So if you go to n+1 parameters, you actually have a corresponding result with a convergence rate. Of course, then the convergence happens only in a certain slab that actually gets thinner and thinner and goes, I mean, in your direction, goes towards the vertical axis as the number of points increases. But at the very least, with n+1 parameters, you don't have to choose delta. And here's finally an illustration of this convergence result where well, it's a little bit fancy, but we chose to use a Brownian motion F on the unit segment on the real line. And we sample the real line uniformly with k points, okay, at random. Regularly, sorry, not at random. So the points really are regularly spaced along the unit segment. And then, so for k equals 50, we get this graph on the left. The value of the graph is the value of the function. So it's the value of the Brownian motion. So from one point to the next, you actually add some Gaussian noise, basically. Okay, and so and so then we studied so we used our estimator phi, the complete phi actually, not phi delta. We didn't choose a slice delta. We actually used phi as an n+1 parameter module, and we looked at the distance between that n+1 parameter module and the Kahn extension of the persistent homology of the Brownian motion, which is now it's work by Baryshnikov and Weinberger, typically, and there was some follow-up work by Chazal and one of his students, and so we know what the barcode of the Brownian motion is. So we can really measure the the distance between our persistence module, our estimator, and the ground truth. And as you can see, as the number of points increases, of course, the distance between the estimator and the target diminishes, and it diminishes, at a rate which is fit by this line, which is log y. So this is a log-log plot, and we have log y equals 1/2 of log x plus some constant. And this is exactly what is expected, because here we have a function f which is not Lipschitz, but it has a modulus of continuity, and our results actually work in this setting. And the modulus of continuity is given by t to the 1/2. So now if we go back to the previous slide, b equals 1 because we're on the unit segment on the real line. And so in principle, the upper bound we should get here would be log k over k to the 1, okay, so log k over k, but then there's the modulus of continuity here that applies, so it should be a square root of log k over k. So now if you represent it in log-log scale, you should see a line with slope minus 1/2, and that's exactly what we see here. I mean, the fit is pretty good, actually. And with this, I'll stop and take questions.